So let's look at a rational function. Now, you can jot down information about a rational function really in any order you want. I just have an order I always use so I don't forget to do something. But if you look at this rational function up here and you immediately observe that the degree on the top is the same as the degree on the bottom, and you just want to write down that since the degrees match, you have a horizontal asymptote that is the leading coefficient of the top over the leading coefficient of the bottom, and just get that horizontal asymptote done right away, you're welcome to do that. That's okay. You don't have to do everything in the exact same order I do. I just do it in a set order, as I said, so I don't forget to do things. One of the things I do is if my rational function is not factored on top or the bottom, I do sometimes try to factor it because I'm going to need to factor the bottom to determine the domain. I'm going to need to factor the top to find any x-intercepts. So I might as well go ahead and factor this right now. And the top does factor as x minus 3, x minus 3. So if you're still struggling with factoring like that, that might be something you want to talk to Rachel and me about before the exam so we can help you with just some of the basics of factoring. And x minus 1 and x minus 5. And all this tells us stuff, it just tells us different things. For instance, x minus 1, x minus 5 on the bottom tells us that our domain is everything except the number 1 and the number 5. Therefore, our two vertical asymptotes are going to be at x equals 1 and x equals 5. Next, I set the top equal to 0, and the reason I set the top equal to 0 is because I'm looking for the x-intercepts. And since it's already factored, most of the work is done. Because when I set the top equal to 0, I can see that there's only one real 0, it's 3. So therefore, 3, 0 is my x-intercept. The next observation I make is that I did not kick 0 out of my domain. 0 is in the domain. So the way I find my y-intercept, the way you always find a y-intercept, is you plug 0 in for every single x. Now if you plug 0 in for every single x, what's the only thing that's not going to go away on top? On the top, the only thing that can be left is the 9. And on the bottom, the only thing left is going to be the 5. So we get 9/5. And if you're uncomfortable with 9/5, that's okay. You can write that as 1.8 if you want. If you want to put that in a calculator, just to get a better idea what it is. Or you can write 9/5. I don't mind if you use fractions or decimals or fractions, as long as the decimal and the fraction are exactly equal to each other. So once we have our y-intercept, our x-intercept, our horizontal asymptote, our domain, and our vertical asymptotes, we are ready to start drawing a graph. And even if you completely freeze up when you draw a graph, maybe just get the asymptotes in there, and if you get the asymptotes in there, maybe everything will start to look better after that. All right, so I'm going to put some dashed vertical lines in here. I'm going to put one at 5 and one at 1. So there's my vertical asymptote at 1. And there it is at 5. So I'm going to write, x equals 1, x equals 5. And I do have a horizontal asymptote of y equals 1. I make the observation that I'm going to have 3 pieces to my graph. 3 pieces because we have 2 vertical asymptotes. That's what determines how many pieces you have. Do I have any ordered pairs? Yeah, I have a couple ordered pairs. I have one right here at 3, 0. That's the x-intercept. It's the only one. And then I have another one at 0, 1.8. So just under the 2 there, right there. All right, now I got to draw 3 pieces to this graph, and I do remember that the asymptotes kind of guide me when I draw these things. So I do want to hug my asymptotes. Hug my asymptotes. All right. So We've done something like this before. One of the most important things about the x-intercept is knowing that not only do we have an x-intercept here, but that is the only x-intercept. So there is only one place we may touch the x-axis. And that actually helps us draw the rest of it. Because if I start over here, the big question is, am I hugging the graph up here with these asymptotes like this, or am I doing it down here? But which one does it have to be, the top one or the bottom one?
Bottom.
It has to be the top one, because otherwise, wouldn't we hit the x-axis again? That's okay, that's why we do it in class. Wouldn't we hit the x-axis again if we did the bottom one? So that one can't be it. So it must be that top one up there in order to avoid the x-axis. Over on the far left side, there's actually two reasons that we do it up top. One of them is we can't hit the x-axis, can't touch x-axis over here, and must hit the y-intercept. So not only can I not put it down here because that would hit the x-axis, but I got to put it up here so I can go through my y-intercept that I know I have. So therefore, I draw another piece of the graph up here, hitting that y-intercept right there. Are these things allowed to touch a horizontal asymptote? We can touch a horizontal asymptote, so we cannot just make a guess of what it does in here and say it must go down because we can't touch the horizontal asymptote. Now, you also don't really want to try to apply rules that apply to polynomials to rational functions. Some people might say to me, Steve, this x-intercept had a multiplicity of 2, so doesn't that mean we're going to bounce? And I would say, yeah, it actually does mean we're going to bounce at that x-intercept, but in general, it's very dangerous because there are two different types of functions to try and apply polynomial rules to rational functions. Because yes, sometimes they do work, but other times, if you're trying to apply rules from one set of functions to another set of functions, you get in big trouble. So just to be on the safe side, what I do, everyone, is I plug both a 2 and a 4 into the function, because those are the two x values right near my intercept, and I can determine if I'm above or below. I find those two ordered pairs. So if you plug a 2 in, if you don't mind, just to save a little bit of time today, I will just tell you you're going to get a negative 1/3. And whatever's easiest for you is what you should do by plugging it in. What I mean is, you can either plug the 2 into this version here, or the factored version here. And either way, you are going to get negative 1/3. And if you plug in 4, you should also get negative 1/3. So yes, indeed, we do have a bounce below, but it didn't have to be below just to avoid the horizontal asymptote. It just happens to be that that's where the points are. So we draw this shape down here that we remember is absolutely not a parabola, but some people think it kind of looks like one. And yes, this right here is indeed a bounce, just like we see with polynomials. But in general, we don't want to try and apply polynomial rules to rational functions. But that is the reason that bounces. And there's a picture of a rational function. I'm not going to tell you these are easy, but I will tell you if you practice them, you have a good shot of doing well in the exam. Because once you get those asymptotes in there, and if you practice them enough, you kind of remember it hugs the asymptotes, then maybe you can start generating a graph. Okay. Questions or comments on that one? As usual, I'm recording this lecture, so if you need to watch that again, you can, of course. All right. Let's do another one. Okay, got my rational function here, polynomial on top, polynomial on the bottom. And then I remember, before I get overwhelmed, it's really only about 5 things I need to find before I go to the graph. I gotta find the domain, horizontal asymptote, vertical asymptotes, x-intercept, y-intercept. And maybe I have all those things, and maybe there's a couple things I don't have. I think I'll start by factoring the bottom. I actually can't really see how to factor the top right now, so I'm just going to factor the bottom, and that's going to be an x plus 3, x minus 2. Remember, if you're kicking out multiple numbers using interval notation, you got to make sure you jump over them in the right order. The 2 bad numbers are negative 3 and 2, so I got to make sure I jump over negative 3 before I jump over 2, because negative 3 is the smaller number. If you can get that domain, can you also get your vertical asymptotes? Yeah. Absolutely you can. The vertical asymptotes are x equals negative 3 and x equals 2. I have a degree match again. The degrees match on the top and the bottom. So my horizontal asymptote, it's y equals 2 over 1, but of course we'll just think of that as y equals 2. Divide the leading coefficients. 2 over 1. All right, that's 3 of the 5 things. Domain, vertical asymptote, horizontal asymptote. X-intercepts. Set the top equal to 0. And as soon as you can tell that your zeros in the numerator are imaginary, you can stop. Because I don't actually care what the zeros are if they're imaginary. Because if I subtract 6 from both sides, and I'll take this one more step and divide both sides by 2, can everyone see how I'm going to get imaginary zeros? Because I'm about to take the square root of a negative. And yeah, in the earlier sections, we cared what those imaginary zeros are. But in this section, we're specifically not looking for zeros, we're looking for x-intercepts. And if the zeros are imaginary, they're not x-intercepts. So right here, I can say no x-intercepts. And now that we've done about 3 of these things, we actually realize that no x-intercepts is actually a good thing. Doesn't that usually help us draw the graph? Because we know we can't hit the x-axis. So actually, this does not bum us out at all. We're like, that's good news. That's very good news for us. The y-intercept, never make the y-intercept more complicated than it has to be. You plug in a 0 for every single x and you simplify. What's the only thing left on top? You plug a 0 in for every x. 6. What's the only thing left on the bottom? Negative 6, which means our y-intercept is going to be 0, negative 1. And that right there is enough to draw the picture of our graph. So let's get my coordinate system up here. Sorry, I should have shrunk down this picture before class, but I did not. Let's see, I did have 2 vertical asymptotes. They were at negative 3 and 2. So let's get those in there. That's not great. Well, I shouldn't have done a dashed line. Okay. So that's x equals negative 3, x equals 2. What else did I have? Did I have a horizontal asymptote? Yeah, y equals 2. No x-intercepts, so remember, we're going to have 3 pieces because of the 2 vertical asymptotes. And avoid the x-axis, hug asymptotes, and I had 1 y-intercept, which was at 0, negative 1. You'll never have more than 1 y-intercept. So for this one, everyone, for this one, is the middle part actually easy? Because we know we have a point down here below, and are we allowed to go over that x-axis? No. Now here's something very interesting to everyone, and we're drawing sketches, so I don't care if you show this detail or not, but I do want to make you aware of it. There is no guarantee that this point right here, the y-intercept, is the highest point on this middle piece. Now if you draw it like that, it's okay, but actually what's going on here, everyone, is this looks a little bit more like this. So that point is not actually the highest point in there. If you draw it like that because you're drawing a sketch, that's fine. But just be aware, the y-intercept is not the highest point on the middle piece. And then I'll say it's okay not to know that.
And is that because the graph isn't centered over
That's how I know it isn't, yes, because it's not centered, because our asymptotes are not at equal distance. Yeah, that actually is how I know that. And if anyone's interested, you actually take a course called Calculus later, and they'll teach you exactly how to find out where that highest point in there is. It's pretty cool. But in this class, we just don't have the machinery to do it, unless we just want to start testing tons of ordered pairs. But I don't want to sit up here, for the next hour and plug ordered pairs into this function. How hard is it to draw the rest of this graph, knowing this right here, avoid the x-intercept? Or avoid x-intercepts. Is this hard?
no?
No, I think we just have a piece up here. And we have a piece over here. Now, why did Steve do this? Why did I draw it like that? It looks like I crossed right over my horizontal asymptote. Why would I do that? It turns out that this graph actually does cross its horizontal asymptote. Did we say it was okay for that to happen?
Yeah.
Here is how I know this graph crosses the horizontal asymptote. Does g of x equal 2x squared plus 6 over x squared plus x minus 6 cross the horizontal asymptote at y equals 2? That's the question. Now, this is not something we do a whole lot of in this class, but this is an interesting thing to observe, and part of this is not just showing you the easy way out, but showing you what's actually happening. The way you answer that question, everyone, is you set the function equal to the number of the horizontal asymptote, and you solve for x. This is how you find out if this function ever hits this line. How do you solve this for x? What does every math student hate that starts with F? We hate fractions. Do we hate fractions? Most of us do. So kill the fraction. Multiply everything by that denominator. And you will get 2x squared plus 6 equals 2 times x squared plus x minus 6. Distribute. And simplify. And there's a really beautiful simplification you do right here. Does everyone see it? What can cancel on both sides? The 2x squared. You can subtract that 2x squared from both sides. It's wonderful. And if you do that, if you subtract 2x squared from both sides, you get 6 equals 2x minus 12. If you add 12 to both sides, you divide both sides by 2, you will get x equals 9. X equals 9, and we already know that y equals 2. Which means, I'm sorry, yes, we do know that. And that means we know that this graph up here, I sort of missed it when I drew it, actually crosses the horizontal asymptote. Now, that is not a detail we often show in this class. So I do not expect you to, every time you do one of these rational functions, to do this analysis. But I wanted to show you it can happen, because I keep crowing up here about, hey, we can hit the horizontal asymptote. That can happen, everyone. That can happen. And I wanted to show you how I can know when it happens. And the way you know it happens is you set the rational function equal to the horizontal asymptote and you solve. So we don't do this very often. But it is possible to do that. It is possible to do that. It's kind of interesting. It still gets close to the horizontal asymptote. What it does, everyone, is it goes down below it and then just comes up at it very slowly from below. These rational functions are treacherous. A lot going on with them. Let me show you one more. Let me show you the one that drives people crazy because it doesn't seem to really give them anything to go on. I would love it if this worked. All right, f of x equals 8 over x squared plus 2. Is that a rational function, everyone? Looks like one to me. Not a very complicated one, but we're allowed to just have a number on top. And we've got at least some x's on the bottom. We got a polynomial on top, polynomial on the bottom. This is a rational function. So I guess the first thing I do is my domain. Does anyone know the domain of that just by looking at it? It is negative infinity to infinity, and I'll tell you why, everyone. This comes up enough in this class, I'm going to make a little rule for you. If the denominator is ever x squared plus a positive number, that means your domain is going to be negative infinity to infinity because your zeros down there are imaginary. So if you ever have a denominator that's x squared plus a positive number, x squared plus 4, x squared plus 9, x squared plus 1, x squared plus 2, you can actually say right away that your domain is negative infinity to infinity. And why am I doing this problem? Because what happens if the domain is negative infinity to infinity? What don't we have?
Horizontal asymptote, or vertical.
Vertical asymptotes. Very good. No vertical asymptotes. Horizontal asymptote. Check this out, everyone. We do have a horizontal asymptote, and I'll tell you why. And this is something I haven't mentioned in a while. I did mention it once a long time ago, but it's easy to forget. What we have, everyone, is we have a degree 0 over a degree 2. If you have just a number, that's considered a degree 0 polynomial. But the most important thing about this, degree 0 over degree 2, is bottom is larger, which means we have the horizontal asymptote y equals 0. So we do have a horizontal asymptote right on the x-axis. That's always the horizontal asymptote if the degree on the bottom is larger. There's no math to do. It's just the degree on the bottom is larger, y equals 0. X-intercept. Set the top equal to 0, and then stare at that for 3 hours and wonder what to do. The question is this. At what point in the universe does the number 8 equal the number 0? Never happens. The top of this will never be 0, therefore this thing will never be 0. So, since this never happens, we have no x-intercept. We're used to that. We've seen a couple that have no x-intercept, so we can handle that. Y-intercept, plug in a 0 for every x. Don't make this one harder than it has to be. What's 8 divided by 2? 4. We do have a y-intercept of 0, 4. The problem is this, everyone. That's all we get. We've done the 5 things. We did domain, we did the asymptotes, we did the intercept. So when it comes time to draw our graph, and I get all set to do it, and I get set to put all the information I've accrued on here, it's going to look like this. Can you see why this would be frustrating after all we've learned? Yeah, what the heck do you do with this sucker? Now, there is a couple things we have going for us. Let me tell you a couple things we have going for us. Our function is f of x equals 8 over x squared plus 2. And because we have no vertical asymptotes, our graph is all going to be one piece. That's good. We're just going to draw one piece. More importantly, everyone, I want to show you something. If I do f of negative x, if I change the x in there to a negative x, it just gets squared away and goes back to being x squared plus 2 again. What does that mean? You want to remember what that means? It's symmetrical. Symmetrical over what? You remember? Y-axis. Y-axis, yes. In other words, this function is even, everyone. This function is even, which means whatever happens on one side is happening on the other side. Now, I know what's going to happen here, everyone. I'm going to have to plot some points. But here's the cool thing. If it's even, I only have to plot points on one side. Does everyone see that? Because I'll just get a mirror image on the other side. And it turns out, this is not the worst thing to plug numbers into. Because if I just start plugging in numbers, like 1, I'll get 8/3. If I plug in 2, I will get 8/6. If I plug in 3, I will get 8/11. If I plug in 4, I will get 8/18. What's the top going to be no matter what number I plug in there? 8. What's the bottom going to do? Keep getting what? Keep getting bigger because we keep on squaring them, right? That's exactly what's going to bring us down to that horizontal asymptote. Also, are these things ever sharp and pointy? No. So here's what we're going to do. We're going to say 8/11. So if I put in a 1, if I put in 1, I got 8/3, which is going to be 2 2/3. So right around here, just doing my best. Put in a 2, I get 8/6, which is 1 1/3. Just doing my best. 8/11, that's a little less than 1. Keeps getting smaller and smaller and smaller and smaller. Do we see the shape? Does it have to be kind of curvy and smooth? So how about this? Good, Stephen. That looks exactly like an even function. A little better. Done. Now, these are not the ones that come up all the time in this class either, but we do need to remember this rule for ourselves, and that is, if you don't know what the graph looks like, you start plugging in numbers. And it turns out it's not always as bad as you think it is. Plugging numbers into this, there's only one x in the entire equation. This is not the worst thing to plug numbers into. And even if you did not make the observation it was even, you would have found out pretty quick it looked the same on both sides because you would have realized that when you plugged in -1, -2, -3, -4, since you were squaring them, you were going to get the exact same y values back out. So even if you didn't sit down at your table and say, I know this is an even function, you would have figured that out pretty fast, that it was an even function. Okay, so that is a rational function. Sometimes they come all in one piece. All right. So, what is up with vertical asymptotes? Last time I taught you how to find a vertical asymptote, and I taught you how to draw them and how to kind of wash up against them. But what is a vertical asymptote? In other words, what makes the graph do what it's doing? Why, when we get close to a vertical asymptote, on one side do we go up, on one side we go down, or do we go up on both sides or down on both sides? What makes this happen? This one has its vertical asymptote at x equals 3, because the equation for this one is y equals x plus 4 over x minus 3. It's undefined at 3, that's where the vertical asymptote is. So it's easy for me to stand up here and tell you that as we get close to a vertical asymptote, the graph's going to shoot up or down. But what I wanted to talk about with this was this. The only number we can't plug in is 3. And granted, while you're looking for ordered pairs of a graph, you usually stay away from fractions and decimals. In other words, usually when you're trying to plot points, you don't say, oh, I think I'll plug in 3.2 today. No, you say I'm going to plug in 4, 5, 6. You want to plug in some smaller ones? 2, 1, 0. But what happens as we get close to this thing? Well, I made a picture here, everyone, just so you could see this. And I wouldn't bother trying to copy this down. This is just something for you to look at later, or look at now. This is that function. And what I did was I realized I can't plug a 3 in there, but I can plug in numbers very, very close to 3. Am I allowed to plug a 2.9 in there? Can I plug in a 2.99? 2.9999999? Yeah, the only number I can't plug in is 3. So what I wanted you to notice is that as I'm plugging these numbers, as x is approaching 3 from the left, as x is approaching 3 from the left, in other words, we're talking about numbers barely smaller than 3, like 2.9, 2.99, 2.999. What are the y values doing? Negative 69, negative 699, negative 6,999. They're shooting down towards where? Negative infinity. That's why the graph is doing what it does. It's not some sort of magic. These graphs are made up of an infinite number of ordered pairs, and usually the ordered pairs that we plot are just nice, clean integers. But if you start putting in these decimals that are extremely close to the asymptote, which is exactly what this means, approaching 3, getting close to 3, then you're going to start getting these numbers. The other direction, when you start plugging in numbers as you're coming at 3 from the right, so when x is approaching 3 from the right, and you're talking about 3.1, 3.01, 3.001, you start getting these enormous y values that keep getting bigger and bigger and bigger. In other words, y is approaching positive infinity. So it's not just arbitrary if it goes up or down. It's not me just saying, that's how it works, deal with it. What is actually happening is, every single point on this graph is an ordered pair on this graph, generated by plugging in an x value and getting a y value. And when you happen to plug in the x values that are very, very close to the vertical asymptote, you are either getting these very, very small y values, like this one, or these very, very large y values, like this one. And since I could get as close to 3 as I want, this negative 6,999, this will just keep getting smaller and smaller and smaller as I put in more 9s on my 2.9999999999999. And as I keep slipping more zeros in here to get 3.000000000000001, this will just keep getting bigger, this 7001, up to infinity, down to negative infinity. So vertical asymptotes make sense. It just requires a little bit of looking under the hood to see why they do what they do. I think that's kind of cool. All right. What's up with the horizontal asymptote? Why does that work the way it does? Well, let's talk about that one. We'll start with this one. Here's a picture of part of a rational function, and the horizontal asymptote is right on top of the x-axis. The horizontal asymptote for this one is y equals 0. And the function, in case you can't see it, let me recopy it because I know that's kind of small. I apologize. Looks like this. Now, the reason the horizontal asymptote is at y equals 0 is because the degree on the bottom is bigger. That's why we get that horizontal asymptote. And the horizontal asymptote doesn't have anything to do with domain. It has to do with what happens as x approaches infinity, or as x approaches negative infinity. Now, this is a little bit hard to say without getting too wordy, but this is what I want to say. Whether you're approaching infinity or negative infinity, your numbers are getting larger in magnitude, and that just means they're getting farther and farther from 0. Now what happens, everyone, is as you start putting larger and larger magnitude numbers into this equation, the +6 and the +5 don't really matter. It's like this, everyone. I don't know what the lottery's up to now. What is it, like 650 million or something? Someone must know that. Something like that? I don't know. 650 million. Unless you're Scrooge McDuck, If they give you $650 million, you don't really care if they give you $6 more. Because that 6 just doesn't matter. And 3x squared is going to get huge. Does everyone agree with that as we keep on putting in bigger and bigger numbers? And that 6 is just going to stay as a 6. In fact, the 3x squared gets big so fast that even the minus 8x doesn't matter. So what happens is, as x approaches infinity, or x approaches negative infinity, the only things that really matter in this equation are the 3x squared and the x cubed, because the other terms don't matter. And if you're only looking at these two terms, which one's getting bigger faster? Cubing a number or squaring a number? Cubing. Does everyone agree 1,000 cubed is much bigger than 1,000 squared? How about 1,000,000 cubed versus 1,000,000 squared? So what happens is, and another way to see this is to cancel, this thing just starts going towards 3 over x. And as x gets huge, this thing goes to 0, which is exactly why this thing goes down to the horizontal axis. Now this is more of a calculus concept, so I don't want you to go home with a headache because of this, but it was my responsibility to show you this so you wouldn't think that horizontal asymptotes were just magical hand waving. What's actually happening is since the numbers are getting so big, the only thing that matters is the largest x power you see here. That's what's going on. So, as x approaches infinity or negative infinity, the only x that matters is the one with the largest power. And since when the one with the largest power is on the bottom, the denominator gets enormous, and the whole thing goes to 0. Here's what actually happened, everyone. Where is it? There it is. Here's what actually happens, everyone. You plug in a 0, a 1, a 5, a 10, not much really to notice here, but as I get in large numbers, 50, 100, 1,000, you will notice that this thing right here is approaching 0. It's getting very, very close to 0 because that x cubed on the bottom is winning. As you put in negative 10, negative 50, negative 100, negative 1,000, this thing is approaching 0. Why? Because the x cubed on the bottom is winning. So we just keep getting closer and closer and closer to the x-axis. That's why the horizontal asymptote works the way it does. I think that's cool. This one's got its horizontal asymptote somewhere else. It's got it at y equals 3. The function looks like this. But as x approaches infinity, or x approaches negative infinity, the only thing that matters is the x squared on top and the x squared on the bottom. They're winning. They don't care about the minus 8x or the plus 6 or the plus 6 or the plus 5 because they get to square their numbers. And as you get really, really big, squaring just dominates the whole thing. So as we get bigger and bigger and bigger, this equation basically starts to look like this. 3x squared over x squared. Only the x squareds matter. If you cancel the x squareds, what does this equal? This thing just starts to look like the number 3. It gets closer and closer and closer to 3, the horizontal asymptote. Why? Because the x squareds take over, and since the x squared on the bottom can compete with the x squared on top, sure enough, we get a table that looks like this. Whereas wait, is that my vertical one? Yeah, that's my vertical one. We don't get a table that looks like that. Sorry. This one. As we go out, this number, as we get out here to 1,000, we can see that this number is getting closer and closer to 3. And as we go out to negative 1,000, we can see that this number right here is also getting closer and closer to 3. One's coming at it from below, one's coming at it from above. But as we put in these bigger numbers, either towards infinity or negative infinity, we are approaching that horizontal asymptote. Why? Because the x squareds are keeping up with each other, but the one on top, in this case, will always be 3 times as big. That's why we divide the leading coefficients. When the degrees match, because they can keep up with each other, we put in larger and larger values of x. Okay, so don't worry about this too much as far as your exam goes. I'm not going to make you fill out tables like this on the test. It takes a while, but it was my job to make sure you understood asymptotes a little bit more than me just saying this is how you draw them. They do make sense mathematically. All right, last thing before we take a break, everyone. In our last class, I drew this sucker for you. Now we can draw it on our own. We can draw this on our own now. Why? Because we know the domain. The domain is everything but the number 0, because you can't put a 0 in there. And if we know the domain...
You don't have x-axis?
I'm sorry?
X-axis?
If we know the domain, we also know the vertical asymptote. And what is the vertical asymptote? We know the vertical asymptote, which is going to be x equals 0. Now, the reason we have the x-axis as an asymptote, which I think you were saying, is because that's the horizontal asymptote. The horizontal asymptote we have because the degree on the bottom is larger, so we get a horizontal asymptote of y equals 0. X-intercept, none, because 1 cannot equal 0. Y-intercept, none, because 0 is not in the domain. And that is why, yeah, I guess I'll draw this one by hand. We get these two asymptotes of x equals 0 and y equals 0. And then, just like we did in class last time, whether you remember or not, you can just plot a bunch of ordered pairs. But really, since we know it hugs the asymptotes, the only really 2 ordered pairs we need to do is observe that when we plug in a 1, we get 1. And when we plug in a negative 1, we get a negative 1. So we have a point here, we have a point here, and we hug our asymptotes. And just like that, we can sketch that function. One that you also see come up is its best friend. Actually, I don't know if they like each other. But its best friend is this one right here. 1 over x squared. 1 over x squared has the same domain. You can't plug a 0 in there. It has the same vertical asymptote, x equals 0. It has the same horizontal asymptote, y equals 0, because degree on bottom is larger. This one also has no x-intercept and no y-intercept. The big difference between the one up there and this one right here is this one. All y values are positive because of the x squared. So this one, no matter what number you plug in there, you're going to square it. So that means both plugging in positive numbers and negative numbers give you positive results. Which is why this graph looks like this. This graph happens to be even. This graph happens to be odd. This graph down here has a range of 0 to infinity. We can observe that by looking at the graph, that it's always above the x-axis but never touches the x-axis. And this one is both above and below but never touches the x-axis, so this one has a range of negative infinity to 0, 0 to infinity. So these two functions, 1 over x and 1 over x squared, actually come up quite a bit, so I just wanted to make sure you had them in your notes. They're friends. I've decided they are friends. So for your records, just so you would have them in your notes, I did put in the two computer-generated images of the graphs after we went to break, just so you can see exactly what they look like and not just rely on my crude drawings of them. And that's going to take us to section 3.6. So we're going to call 3.5 done. And we're going to do section 3.6. Which is all about polynomial and rational inequalities, which sounds awfully wordy and complicated, but really what we're doing in this section is this. With an equation or a graph of a polynomial or rational function, can we use interval notation to describe when, I'll say where, the graph is above or below the x-axis. That's really what this section is about. Maybe that doesn't sound any simpler to you. With an equation or a graph, either one, it's a polynomial or a rational equation, can we decide, using interval notation, how to tell people when that graph is above or below the x-axis? So, we'll start like this, and this is going to be similar to the pre-work you did, this first example. So I want to start with something that you've already kind of seen. So we'll just put a nice quadratic up here. And the most important thing about this parabola right here, which I will call f of x, is that it has its x-intercept here at negative 5, 0, and its other one over here at 1, 0. So if someone said to me, give the x values where f of x is below the x-axis, then I just look at the graph and I say, look, there's pieces of the graph above the x-axis, there's pieces of it below the x-axis. Where is it below? Right here. And what two x values am I in between right there? Negative 5 and 1. So the answer to this is negative 5, 1, like that. That's an interval, everyone, not an ordered pair. If someone said, give the x values where f of x is below or touching the x-axis, then I would do the brackets. That's absolutely right. Yes. Because that's where it's either below or touching. That's what this section is all about, everyone, is deciding whether your graph is below or above and giving an interval notation where it is. The other two questions they might ask would be above x-axis, above or touching x-axis. If they want to know where it's above, it's a little bit more complicated than below, because I got to do this one with two different intervals, because it's got a break in the middle. Does everyone see that? So negative infinity to negative 5, and 1 to infinity. And just like before, when it's touching, we will use brackets to say at those two intercepts it's actually touching the x-axis. That is the core concept of this section of 3.6. Now I'm not going to tell you the problems are going to get more difficult, but these are the questions we need to understand how to answer. Above, below, above or touching, below or touching.
So it's just the x-axis, isn't it?
Yeah, we're talking about we're not talking about when we're to the right or left of the y-axis, just when we're above or below the x-axis. Yes. So I made this little thing before class. I thought it might help. Oops. So if they're asking you where your function is greater than 0, that means above. If they're saying greater than or equal to, that means above or touching. If they say below, if they say less than 0, that means below the x-axis. If they say less than or equal to 0, then it's below or touching the x-axis. So those are the inequalities you want to look out for, and that tells you in words what those inequalities mean. And we're going to give all of our answers in interval notation. All answers in interval notation except when answer is a single number. That could happen, everyone, if a graph like touches and then turns around. So it doesn't actually go below. For instance, if I said when is f of x equals x squared less than or equal to 0, what I'm asking you is I'm asking you when is that below or touching the x-axis? Well, was it ever below the x-axis? No, but is there a point where it's touching the x-axis? Yes, so the only answer to this would be 0, because we're touching, but never below. And this wants to know if we're below or touching. And we are touching at one point. What I think you noticed in the pre-work is that almost all the problems you did dealt with giving you a picture. In the build understanding homework, you're going to be working with equations more than pictures. So just so you know where we're headed, the pre-work was doing this with pictures. I guess I should say graphs because this is a math class. And the build understanding, which we'll be working on over this weekend, is going to be equations. And the big idea with the equations is we try to avoid sketching the entire graph. We're going to do our best to avoid actually just having to draw the entire picture. Because if we're going to draw the whole picture, then we might as well be back in a different section where we're drawing graphs. All right, so here's what a question might look like. What we see here is we see a factored polynomial, and we see a greater than 0. So really what this is asking is, when, I should say where, because I'm doing the x values, sorry. Where is the function f of x equals x plus 3, x minus 1 squared, x minus 5 above the x-axis? Answer with x values using interval notation. So what we're going to do is we're going to use whatever kind of machinery we have to answer this question without actually having to draw the entire graph. So let me just bring up something here that's a little bit easier than a graph. let me just bring up a number line, or in other words, just the x-axis. Just the x-axis. And let me mark on this x-axis all of my zeros that go with this factored polynomial. In other words, -3, 1, and 5. Everyone okay so far? Let me also put a little C right here, a little B right here, and a little C right there. Who knows what those stand for?
Cross, bounds, or cross.
Cross, bounds, and cross. Okay. Now, let me think about this thing. It is a 4th degree. Let me do that down here. It is a 4th degree with a positive leading coefficient. 4th degree. It either goes up on both sides or down on both sides. If it's a positive leading coefficient, what does this one do? Up on both sides. Everyone agree with that? So that means on either end of the graph, because it goes up on both sides, this thing has got to be above the x-axis. Does everyone agree with that? It's got to be if it goes up on both sides. If you cross over the x-axis, then you're switching which side you're on. So these red pluses mean we're above. But if we cross the x-axis, what are we? We're below. And if we bounce, and if we're below and then we bounce, are we still below? And that is one way to determine whether or not you're above or below the x-axis. Now we go back and look at the original question. It wants to know, when are we above the x-axis? So, my answer looks like this. From -infinity up to -3, and from 5 to infinity. And I use parentheses because it was just a greater than, not a greater than or equal to. Now that is one way to solve this problem, everyone. That is one way to solve this problem. And if that makes sense to you, you're in really good shape. If it doesn't make sense to you, I've got something else for you. Or, same problem again, everyone. Same problem again. Now, however you do this, I do recommend you use a number line. I'm just going to show you a different way to use the number line for this one. So the first thing we do, it's going to start out very similar. In fact, we identify our zeros. And we put them on our number line. Now here's what we're going to do, everyone. I need some test numbers. I need some numbers I'm going to plug into the function to get ordered pairs, and I need a test number from each interval you see up here. So everyone, give me any number you can think of that's less than -3. -4, great. Give me any number you can think of between -3 and 1. You can pick the easiest one if you want. What's the 0? That'll work. I need a number between 1 and 5. 3. And a number bigger than 5. I'll pick this one, 100. Then what you do, everyone, is you take these numbers and you plug them into your equation. Like this. And you analyze if the result is positive or negative. So everyone, I'm going to try and do this in a really slick way, and I want you all to join me, so watch this. Is negative 4 plus 3, is that positive or negative? That's a negative number. That's a negative number. Negative 4 minus 1 is negative 5, but then you square it. And if you square it, what's the result? Positive. Negative 4 minus 5, is that positive or negative? Negative. If you multiply a negative number times a positive number times another negative number, what kind of result do you get? Negative times a positive, two negatives cancel each other. Result? Positive. Here's my promise to you. Any number you picked over here, negative 5, negative 6, negative 7, negative 20, negative a million, negative a billion, if you plug that in here, you're not going to get the same number every time, but I do promise you this. You'll always get a positive answer. So that means, positive means above the x-axis. Now, at this point, class, you can either use the rules of crossing and bouncing to decide if you change, or you can actually plug in all your sample numbers. For instance, I know that we cross right here. And if I cross, what should this part be, above or below? It should be below because we were above. But what you could also do is you could plug a 0 in here. And use 0 plus 3, 0 minus 1 squared, and 0 minus 5, which would give me a positive times a positive times a negative, which is negative, which is below. Why would we ever do this instead of just drawing the picture? The reason we do this is because sometimes the pictures are much harder to draw than to make this number line. And once you get this number line system down, it's actually pretty fast. If we continue, we will get this and this. And you could use the bounce and the cross. And the reason I keep bringing that up is because I don't want you to forget what you already know when you're doing a problem. There's nothing wrong with using your previous knowledge to help you solve a new type of problem. So, let me show you a really, really slick way to use this number line and this technique with the sample numbers. And it's really, really smooth. You'll like this. Let me show you something. You get to a problem that looks like this. You say, okay, gotta figure this out. Here's what you do. First, you mark your zeros on the number line. Which one do people often forget on this one?
0.
0, but it's right there because there's an X in front. So you mark 0, you mark -2, and you mark +3. Then you come up with 4 sample numbers. In this case, -3, -1, 1, and this time I actually will use the 100. Now let me show you something neat. What we do is we plug each one of those sample numbers into our factors. And what we're going to try and do is see if we get something positive or negative, and that will tell us if we are above or below the x-axis. So class, watch what I do here. If you put a -3 in for x, that's going to be just a -3. What's -3 plus 2? Positive or negative? Negative. What's -3 minus another 3? Negative. If you multiply a negative times one more negative, what's your result? It's a negative. Remember, everyone, 2 negatives multiplying equals a positive. An odd number of negatives multiplying equals a negative. Ever remember all that from your arithmetic days? You plug in the -1. Negative, -1 plus 2, positive. -1 minus 3, negative. A negative times a positive times one more negative, there's two negatives, so what's the result? Positive. Remember, even number of negatives, you'll end up with a positive. Odd number of negatives, you'll end up with a negative. Are we okay with that? You plug in a 1, it's going to be positive, positive. What's 1 minus 3? Negative. Result? Negative. 100. 100 in every one of these is going to give you positive, 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 positive. What these tell you, everyone, oh no. No, math. Come back to me, math. Okay. What these tell you is they tell you if you are above or below the x-axis on that piece of the number line. The minus tells me that I'm below. The positive tells me I'm above. Minus tells me I'm below. Positive tells me I'm above. The question this thing is asking me is, am I above or touching? So you look for the ones where the pluses are and you include the endpoints because we're touching there. So our answer would look like this. -2 to 0, 3, and of course never use a bracket on infinity. This is actually a precursor to a skill that you use in a calculus class. That's one of the reasons we teach it in college algebra, because a lot of people that are taking college algebra plan on moving on through a math sequence. I hope you all do, but I know you're not all doing it too. Okay. So the cool thing about solving these problems, though, is you actually don't care what your inequality is until you get to the very end of the problem. That's actually one reason I like these so much. So let's say you were doing one of these problems. So we're going to join an example in progress. Join in progress. In other words, someone had a polynomial, and they have already made that whole chart. They've already filled out their number line. -4, -1, 2, 6. They already know that this one goes plus, minus, minus, plus, minus. So they've done all this work already. They've already filled that out. They know that they have a polynomial that's above, then it's below, it stays below, it's above, and then it's below again. They have all this information. And the really slick thing is, at this point, they can look at the inequality for the first time and decide what information they want to pull off the number line. You see, you can set up your number line because it's basically like a little depiction of what your graph looks like, and then you can figure out the question you're trying to answer. Are we trying to answer where it's above? Well, if I'm trying to answer where it's above, then I would go -infinity to -4 and 2 to 6. Everyone see that? But can I answer all these other questions using that exact same number line? Yeah, I sure can, and that's the beauty of this system. The thing is, it does get a little bit trickier. It gets a little bit trickier. Because when I'm asking where I'm above or touching, it's very, very easy to write this. -infinity to -4 with a bracket, and a bracket with 2, and a bracket to 6. But that is not the correct answer. Why is that not the correct answer? Because -1 is touching. Who said that? Or was that? Oh, nice job. Yes, because it's touching at -1. Did I tell you we're going to be using interval notation in this section? Did I tell you every now and then we would also need to include a single number? That's exactly what we need to do. Well done. So this one is not going to be that, it's going to be this. Because it's touching at -1. And we cannot forget that, because it's not just saying above, it's saying above or touching. And it's very, very easy when we see that equal to, just think, oh, that all I need is now is brackets, and I'm done. Nope. We need to include that -1 in there also. So that being said, see if you, the awesome math students, can answer these last two. See if you can give me the intervals where it's both below and below or touching. So for below, we just want where the negative signs are, but we can't put in where the actual x-intercepts are. Which is why when I'm just doing below, I have to make sure I jump over that -1, because at -1, I'm not below the x-axis, I am touching the x-axis. So I have to do -4 to -1, -1 to -2, and 6 to infinity. When I'm doing below or touching, because I'm touching at -1, I can just gloss right over the -1 and just do a solid one from -4 to 2 with brackets, and then from 6 to infinity with a bracket on 6 and of course a parenthesis on infinity. So these problems have kind of two challenges. One is actually constructing your number line, and then the second challenge is making sure you can actually pull the information you need off of your number line. All right. But if you ever flip out and you're like, I have no idea what to do, remember, you can always try and draw the graph. If you just freak out like in a testing situation, you're like, I don't remember all that stuff he said about number lines and pluses and minuses, that was a nightmare. What if I just sketch the graph? Well, if you have a picture of the graph, you can pull off where it's above and below also. So don't forget the things you already know. The things you already know can help you sometimes. Hopefully all the time. When is x squared plus 4 greater than 0? What does the graph of x squared plus 4 look like? It's a parabola, and what's happened to it? Shifted up 4 units. The graph looks like this. When is the graph of x squared plus 4 above the x-axis? Always. Done. When is it above? It's always above. When is the graph of x squared plus 4 below the x-axis? Never. This is called the empty set. All that means is there's not a single number you could ever plug in there that would make that true. And by a single number, I mean there's no real numbers you could plug in there and make that true. Never happens. This graph is never below the x-axis. When is x squared above the x-axis? Always? Except 0. Shoot. If this is greater than, we are not allowed to include that point where it's actually touching. So the answer would be negative infinity to 0, 0 to infinity. Got to be careful. That's why I do it, so you can be careful later. Okay. What makes this harder? This is what makes this harder, everyone. To do these problems, we must have a 0. By that I mean the number 0 on the other side of the inequality. This problem is not ready to go as it is. This is not ready to go because we cannot have that 2 over there. And while it is heartbreaking that this side is already factored, it doesn't do any good to have that factored if there's a 2 on the other side. So this is what you must do on this problem. Since this is not a 0, we need to multiply out the left, subtract 2 from both sides, and refactor. Very irritating, not on every problem, but there are a couple problems where you might see this. So here's what you have to do. X squared minus x. I got to multiply that out over there. I got to subtract the 2 from both sides. I got to refactor. And now I can do the problem. You cannot do it unless you have a 0 over there. I shouldn't say you can't. I should say it is much, much, much harder. Because this original question is not asking where is it below the x-axis, it's asking where is it below the line y equals 2. And finding where something is below the line y equals 2 is much trickier than finding out where it's negative. So, if you were to make yourself a little number line here, you can either do a bunch of test numbers, or you can remember what a parabola looks like. This is a parabola that opens upward. If it opens upward, is it positive on the outsides or on the inside? Where is it positive if it opens upward? Well, maybe we can't figure that out. So maybe what we need to do is we need to plug some test numbers in. First of all, I don't know how you expect to do this problem when you put those numbers in the wrong places. Who let you do that? It's a number line, number 1. -1 goes on the left, 2 goes on the right. If you take some sample numbers like -3, 0, and 4, what you can do is you can plug those in to the function and see what your results are. What's -3 minus 2? Positive or negative? Negative. What's -3 plus 1? Negative. What's a negative times a negative? Positive. You put 0 in there. 0 minus 2, negative. 0 plus 1, positive. Negative times a positive, negative. 4 minus 2, 4 plus 1, both positive. Result positive. What that means to me, everyone, is it means this thing is positive, 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 negative, 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 positive, positive, positive. I want where it's less than or equal to 0, which means I want between -1 and 2 with the brackets because of the equal to sign. Could someone have also done this problem if they were feeling particularly sassy with their math? Could someone have also done this problem just by graphing the function x minus 2, x plus 1? Just by going like this. Got an intercept here, an intercept here. End behavior is up on both sides. So it looks like that. So I'm looking for this part in here where it's below. Would that have been a valid way to solve the problem? Yeah, it's the exact same thing. It's just another way of looking at it. The beauty of the chart with all the pluses and minuses is it helps you organize your work if for some reason you're not going to have this many, but if for some reason you had 10 x-intercepts. Some bouncing, some crossing and flattening. If you couldn't figure out your end behavior, this would work. And you wouldn't have to draw a whole picture. It's also nice in case some of your x-intercepts were bigger numbers, like x minus 20. You don't have to draw a picture that goes all the way up to 20. All right. Yeah, question?
Would you still have to solve?
Here, is the last type of problem you will see on your exam. It's the very last type of problem you'll see on your exam. A rational inequality looks like this. I'm not saying this is the problem from your exam, I'm saying it's the last type of problem you'll see on your exam. That's why I want to make sure we do it today, because even if we need to finish this section next time, at least we'll be all ready for the test as far as covering material. X plus 3 over x minus 5 is greater than 0. What the heck does that mean? Well, this is a rational function. Here's what we need to know about rational functions. Rational functions are harder to graph. So we should use a number line. Even if for the polynomials we drew pictures, in general it's harder to draw these things. So we're going to use a number line. And here's the most critical difference between doing these problems with a polynomial and doing them with a rational function. Rational functions can cross the x-axis at an x-intercept where the top equals 0, or at a vertical asymptote, which is where the bottom equals 0. The only ways a rational function in this class can get across the x-axis is at an x-intercept or a vertical asymptote. Polynomials can only do it at x-intercepts. That's the only way a polynomial can get across the x-axis, is by having an x-intercept. The only way a rational function can do it is at an x-intercept or at a vertical asymptote. So class of mine, if we have f of x equals x plus 3 over x minus 5, can you tell me just by looking at that where its x-intercept is? Where is the x-intercept? -3 is where the x-intercept is, because that's what makes the top equal to 0. Everyone cool with that? So the x-intercept is at -3, 0. What's important to me is the -3. Where does it have a vertical asymptote? At 5, the value that makes it undefined. So it has a vertical asymptote at x equals 5. Those, class, are the only two places this graph, whatever it might look like, can possibly get across the x-axis and change whether it's positive or negative. So, if I make my number line, oops. If I get my number line, I label these two values on it. -3, because that's an x-intercept, and +5, because that's a vertical asymptote. And what I do now is I figure out where the rational function is, above or below the x-axis, by plugging sample numbers into it. Class, can you tell me a number below -3? Any number below -3? -4 I heard. I also heard -5. I need a number between -3 and 5. Any number you want? 0, 2. I'll do 0. 2 would work. A number bigger than 5?
7.
7. Get your answer in that time. Good job. Okay. Now look at this, everyone. -4 plus 3 over -4 minus 5 is -1 over -9. Is that positive or negative? That's positive. That means, for this part right here, we are above the x-axis. If you put a 0 in there, you're going to get 3 over -5. Is that positive or negative? Negative. That means for this part right here, we are below the x-axis. If you put a 7 in there, you're going to get 7 plus 3 over 7 minus 5, which is 10 over 2, which is positive. Let me be very clear what we know here, everyone. I don't know the exact shape of this graph, but I do know if you were to graph it, and you have the several pieces that you would to a rational function, on this interval it's above the x-axis, on this one it's below, and on this one it's above. That's what I know. And if I know that, can I answer the question, when is x plus 3 over x minus 5 greater than 0? Can I answer that question? Yeah, I know when it's above. Where is it? Negative infinity, negative 3, and then 5 to infinity. Was I right to use parentheses? Yeah, it sure was. So, awesome math, people. See if you can answer this one. By the way, I'm about to try and mess with you. I'm asking you a trick question, everyone. Not a question you shouldn't try to answer, but I'm asking you to answer something I have not taught you about yet. But see if you can answer that one. See if you can answer that one. You can still use the same number line. What Steve's up to? Is he trying to trick us? Maybe you know, but keep it to yourself if you know. If you know my treachery. If you wrote that as your answer, do me a favor and put a big X through it. If you didn't write it as an answer, go ahead and write it as an answer and put a big X through it. Have this with a big X through it on your paper. Who would like to raise their hand and tell me why that isn't the right answer? What do you got?
Because it's still infinite.
What's still infinite? I think I know what you're saying.
So the number line would still be infinite, no matter if that would be equal to or not. It's the fact that it is a equal. It's equal to those two.
It's equal, so I use brackets.
But
anyone want to help out? What's up?
It can't be 5 because of the vertical asymptote?
At a vertical asymptote, are we actually touching the x-axis?
No.
This might have been what you were trying to say. I'm sorry if it was. Oops. You see, I want to know where we're below or touching. Now, this number line does go on forever. You're absolutely right. However, it will stay pluses out here forever, and it will stay pluses out here forever. The thing that we need to watch out for is this is asking when are we below or touching. And we are below or touching at -3, but not at 5. Because at 5, there's a vertical asymptote. And that does not count as a touch. That's just a place where we switch which side we're on. So that's why you do want the bracket on -3, but you want the parenthesis on 5. Because you never get to use a bracket at a vertical asymptote. Let's say that. You never get to use a bracket at a vertical asymptote. At a vertical asymptote, never. So when you're doing these problems, and you have an equal to, the equal to is sort of rings a little bell in your head that says, I must use a bracket now. And that works for polynomials, because the reason that we do polynomials, the reason they have numbers on the number line, is because they're x-intercepts. They're places where we're actually on the x-axis. It's perfect. But when we're working with these vertical asymptotes, we are not actually touching the x-axis there. You see, this graph, what it looks like is it has a vertical asymptote at 5. It has an x-intercept at -3. All right, yes. And it has a horizontal asymptote at 1. Like that. And what the graph does is sort of like this. And if I'm asking where we are below the x-axis, then we are below the x-axis starting here at -3. and all the way upwards towards 5, but we never actually get to 5. And as you can see, our number line did not lie to us because everywhere else we are above. Over here it just stays above, hugging its horizontal asymptote. And over here it stays above. Remember, I'm not talking about if we're above or below the horizontal asymptote. I'm talking about if we're above or below the x-axis. So over here we are above. Over here we are above. And over here we are below. But let me stress this again. What in general is easier? Trying to whip out this picture as quickly as you can, or filling out this number line? Well, I made the picture look easy, but that's because I studied this problem before class. So I knew how to draw it. But if you're just coming at this fresh, you might not know exactly what the picture looks like, and it can give you some trouble. So class, I'll just tell you this. You will see a problem like this on the exam, and it will have either less than or equal to or greater than or equal to, so I can make sure you include the x-intercept and exclude the vertical asymptote. Is that what we just talked about? I'll probably put one of these on the test and put an equal to on it. So just to make sure that you know when to use a parenthesis and you know when to use a bracket. The kind of problem that we need to make sure we can do next time, and I am almost out of time today, but next time, in addition to review, so you can do most of the homework for this section. I'll show you how to deal with this type of situation. What to do if there's not a 0 on the other side. So you should be able to bust out most of your homework for section 3.6. But if you see a problem like this and you want to wait till next time for me to show you how to do it, you can. Or, of course, you can always try it on your own. That's just fine. But I am out of time, everyone, so thank you so much.